Chapter 2: Membrane Architecture. Membranes are the governing structures of the biological system. They are not passive layers that separate compartments. They are engineered materials whose composition determines how the system holds gradients, transmits signals, and regulates exchange under continuously changing conditions. Every membrane operates within a narrow range of physical properties that must be maintained for the system to remain stable. These properties are set by the arrangement of lipids within the bilayer, the presence of sterols that regulate packing, and the distribution of embedded proteins that depend on that environment to function. When this architecture is coherent, the system operates with precision. When it drifts, instability emerges across every process that depends on it. The bilayer forms through the self-assembly of phospholipids, but its behavior is not defined by that assembly alone. The fatty acid chains that make up the interior of the membrane determine how tightly the structure holds together. Saturated chains align closely, creating a dense environment that resists deformation and limits uncontrolled permeability. Unsaturated chains introduce bends that prevent tight packing, increasing fluidity and allowing movement within the membrane plane. This balance between density and mobility sets the operating range for the system. Too much rigidity restricts transport and protein function. Too much fluidity increases leakage and destabilizes gradients. The membrane must maintain a controlled midpoint where movement is possible without losing containment. Cholesterol acts as a regulator within this system, inserting itself between phospholipids and adjusting how they interact. Its presence reduces excessive motion in fluid membranes and disrupts overly rigid packing when membranes become too dense. This stabilizing effect allows the membrane to maintain consistent behavior across temperature changes and mechanical stress. Without this regulation, membranes would fluctuate outside their functional range, leading to unpredictable transport and signaling. Cholesterol does not serve as a passive filler. It sets the boundaries within which membrane dynamics can operate. Membrane architecture also defines how proteins behave. Embedded proteins are not independent units. Their function depends on the surrounding lipid environment. Receptors require specific packing conditions to cluster and initiate signaling. Transporters rely on membrane thickness and fluidity to cycle between conformations. Ion channels depend on local electrical properties to open and close with precision. When the lipid environment shifts, these proteins change behavior even if their structure remains unchanged. The membrane sets the context in which they operate, and any alteration to that context alters the output of the system. Microdomains form within the membrane where specific lipids concentrate to create localized environments with distinct properties. These regions organize receptors and signaling molecules into functional clusters, allowing signals to be transmitted with speed and accuracy. The formation of these domains depends on lipid composition and the presence of stabilizing components such as cholesterol and sphingolipids. When the membrane lacks the materials required to maintain these domains, signaling becomes dispersed. Receptors no longer cluster effectively, and signals lose strength or persist beyond their intended duration. The system continues to process input, but the clarity of that processing declines. The membrane also functions as an electrical barrier. It separates charges and allows the system to maintain gradients that drive transport and communication. The ability to hold this separation depends on the integrity of the lipid bilayer. If permeability increases due to structural instability or oxidative damage, ions cross the membrane without control. The system compensates by increasing active transport, raising energy demand while reducing efficiency. Over time, this leads to a state where energy is consumed maintaining gradients rather than performing useful work. The difference between efficient and inefficient systems is not how much energy they receive, but how well their membranes preserve the conditions required to use that energy. Membrane architecture is continuously remodeled. Lipids are replaced as new materials enter the system, and damaged components are removed or repaired. This process integrates dietary inputs directly into the structure of the membrane. The properties of the membrane therefore reflect the composition of the available lipid pool. Stable inputs lead to membranes that resist deformation and maintain consistent behavior. Unstable inputs introduce variability, increasing susceptibility to damage and altering how the membrane responds under stress. These changes accumulate over time, gradually shifting the operating characteristics of the system. Understanding membrane architecture provides a direct link between material input and system behavior. It explains how structural changes propagate into functional outcomes without requiring separate explanations for each process. The membrane is not one component among many. It is the medium through which all components interact. When its architecture is maintained within its functional range, processes align and produce consistent results. When it is not, variability emerges because the conditions required for coordinated activity are no longer present. Phospholipid bilayers as dynamic systems. The phospholipid bilayer is not a fixed barrier. It is a dynamic material that maintains separation while continuously adapting to mechanical, chemical, and electrical demands. Each phospholipid contains a polar head group and hydrophobic tails, which drives spontaneous organization into a bilayer that shields the tails from water while exposing the heads to it. This arrangement creates a stable interface, but stability does not mean rigidity. Individual lipids move laterally within the plane of the membrane, rotate, and adjust their packing in response to changes in composition and stress. This constant movement allows the membrane to absorb deformation, reorganize local regions, and maintain integrity without fracturing under load. Fluidity defines how this system behaves. The degree of movement within the bilayer is controlled by the composition of the fatty acid chains. Saturated chains align closely and restrict motion, increasing resistance to deformation and limiting uncontrolled permeability. Unsaturated chains introduce bends that prevent tight packing, increasing mobility, and allowing proteins embedded in the membrane to shift position and interact. The membrane operates within a narrow range where movement is sufficient to support function but constrained enough to preserve containment. If fluidity rises too far, the membrane loses its ability to hold gradients. If it drops too low, transport processes slow and protein conformational changes become restricted. This dynamic behavior supports protein function. Membrane proteins depend on the surrounding lipid environment to maintain orientation and cycle through their functional states. Transporters require space to shift between inward-facing and outward-facing conformations. Receptors rely on lateral movement to cluster and initiate signaling. Enzymes embedded within the membrane require consistent local conditions to maintain catalytic activity. The bilayer provides both the structural support and the flexibility required for these processes to occur. When lipid composition shifts outside its functional range, protein behavior becomes inconsistent because the environment no longer supports reliable operation. The bilayer also responds to external forces. Mechanical stress, temperature changes, and chemical exposure all influence how lipids pack and move. Cholesterol moderates these responses by inserting between phospholipids and stabilizing their interactions. When the membrane becomes too fluid, cholesterol limits excessive motion. When it becomes too rigid, cholesterol disrupts tight packing and restores mobility. This regulation allows the bilayer to maintain functional properties across varying conditions. Without it, the membrane would drift into states where either leakage or rigidity compromises system performance. Permeability is controlled through this dynamic structure. Small nonpolar molecules can pass through the lipid interior, while ions and polar compounds require transport mechanisms. The rate at which substances cross the membrane depends on how tightly lipids are packed and how often transient spaces form between them. Increased fluidity raises the likelihood of these transient openings, increasing passive permeability. Decreased fluidity reduces these events, strengthening containment but limiting diffusion. The bilayer must balance these opposing demands to maintain controlled exchange. The bilayer is also subject to continuous remodeling. Lipids are replaced over time as new molecules are incorporated and damaged ones are removed. This alters the distribution of saturated and unsaturated chains, changes cholesterol interactions, and shifts the overall behavior of the membrane. These changes do not occur instantly. They accumulate through repeated cycles of incorporation, gradually altering how the bilayer responds to stress and how it supports embedded proteins. The system adapts to the materials available, and the properties of the bilayer reflect the composition of that material pool. Viewing the phospholipid bilayer as a dynamic system explains how membranes maintain both stability and adaptability. It holds separation while allowing movement. It supports protein function while regulating permeability. It absorbs stress without losing integrity. These capabilities emerge from the physical properties of the lipids themselves and how they are arranged within the membrane. When this arrangement is maintained within its functional range, the system operates with consistency. When it shifts beyond that range, variability emerges because the membrane can no longer provide the conditions required for controlled behavior. Cholesterol as structural regulator, not risk factor. Cholesterol functions as a control element within membrane architecture. It does not sit on the periphery of the system as a circulating liability. It is embedded within membranes where it regulates how lipids pack, how proteins behave, and how the membrane responds to stress. Its structure allows it to insert between phospholipid tails, aligning with them while interrupting excessive movement. This positioning gives cholesterol the ability to modulate membrane properties directly, adjusting fluidity, permeability, and mechanical stability in real time as conditions change. Membranes require a narrow operating range to function correctly. If the bilayer becomes too fluid, transient gaps form more frequently, increasing passive leakage of ions and small molecules. This weakens gradients and forces the cell to expend energy, restoring separation. If the bilayer becomes too rigid, transport slows and proteins embedded in the membrane struggle to shift between functional states. Cholesterol stabilizes both extremes. In highly fluid membranes, it reduces motion and tightens packing, limiting uncontrolled permeability. In overly rigid membranes, it disrupts tight alignment of saturated lipids, restoring mobility. This bidirectional control keeps the membrane within a functional range where containment and flexibility are balanced. This regulatory role extends to protein behavior. Receptors, ion channels, and transporters depend on consistent membrane properties to maintain orientation and function. Cholesterol influences the local environment around these proteins, affecting how they cluster, how they respond to ligands, and how they cycle through conformational states. In signaling regions, cholesterol contributes to the formation of ordered domains where receptors can assemble into functional complexes. When cholesterol levels within the membrane fall outside optimal ranges, these domains lose coherence. Receptors either fail to cluster effectively or remain active longer than intended, distorting signal timing and strength. Electrical stability also depends on cholesterol-mediated control of membrane permeability. Ion gradients are maintained because the lipid bilayer resists free movement of charged particles. When membrane structure becomes unstable, ions leak, and the cell increases active transport to compensate. Cholesterol reduces this leakage by tightening the bilayer, preserving the separation required to hold gradients with minimal energy expenditure. This directly influences how efficiently cells maintain electrical potential and how consistently they can transmit signals across tissues. Cholesterol also affects membrane resilience under chemical stress. Lipid bilayers are exposed to reactive species that can disrupt fatty acid chains and alter membrane integrity. By stabilizing lipid packing, cholesterol reduces the susceptibility of the membrane to structural disruption. It does not prevent chemical reactions from occurring, but it limits the extent to which those reactions propagate into large-scale changes in membrane behavior. This containment preserves function under conditions that would otherwise push the system into instability. The body maintains cholesterol distribution through tightly regulated transport systems. Lipoproteins move cholesterol between tissues, delivering it where structural reinforcement is required and removing excess when balance shifts. This process is not random circulation. It is targeted allocation of structural material. When tissues experience stress or damage, cholesterol is directed toward those regions to support repair and restore membrane integrity. Elevated levels in circulation often reflect increased demand for structural reinforcement rather than a primary cause of dysfunction. Reframing cholesterol as a structural regulator clarifies its role within the system. It is not an external risk factor acting independently of cellular function. It is a component of the membrane that determines how the system holds its shape, maintains gradients, and supports signaling. Removing or suppressing it without addressing underlying structural conditions alters membrane behavior in ways that can reduce stability rather than improve it. The system depends on cholesterol to maintain control over its boundaries, and its presence reflects the need to keep those boundaries within a functional range where biological processes can operate with precision. Saturation, fluidity, and mechanical stability. Membrane behavior is set by how lipid chains pack together. Saturation determines that packing. Saturated fatty acids align closely, forming a dense interior that resists deformation and limits uncontrolled permeability. Unsaturated fatty acids introduce bends along the chain that prevent tight alignment, increasing spacing and lateral movement within the bilayer. This difference in geometry sets the baseline for fluidity, which then defines how the membrane responds to stress, how proteins move, and how gradients are preserved under load. Fluidity is not a target to maximize. It is a parameter that must remain within a functional range. When the bilayer becomes too fluid, transient gaps form more frequently between lipid chains. These openings allow ions and small molecules to pass without regulation, weakening gradients and forcing the cell to increase active transport to restore separation. The system becomes energetically inefficient because it is compensating for structural leakage. When the bilayer becomes too rigid, the opposite constraint appears. Transporters and channels struggle to cycle between conformations, receptor mobility decreases, and signaling becomes delayed or incomplete. The membrane must hold a midpoint where movement is sufficient for function but constrained enough to maintain containment. Mechanical stability emerges from this balance. A membrane built with a higher proportion of saturated lipids maintains shape under pressure, resists shear forces, and limits deformation when exposed to changes in temperature or chemical stress. This stability allows gradients to persist with minimal correction and provides a consistent environment for embedded proteins. Introducing unsaturation increases flexibility, allowing the membrane to adapt to movement and local changes in curvature, but it also reduces resistance to disruption. Each additional double bond introduces a point where packing is weakened and susceptibility to chemical attack increases. The system trades stability for mobility, and that trade must be controlled. Cholesterol modulates this relationship by adjusting packing density in both directions. It reduces excessive motion in highly unsaturated regions and disrupts overly tight packing in saturated regions, maintaining a consistent operating range across different conditions. This regulation allows membranes to remain functional despite variations in temperature and mechanical stress. Without it, shifts in lipid composition would push the membrane outside its functional range, leading either to leakage or rigidity that interferes with protein function. Protein behavior reflects these structural conditions. Receptors require lateral movement to cluster and initiate signaling. Transporters depend on membrane flexibility to change shape and move substrates across the bilayer. Ion channels rely on consistent electrical properties to open and close with precision. When fluidity is too high, these processes lose specificity because the environment becomes disordered. When fluidity is too low, processes slow or fail because movement is restricted. The membrane does not simply host these proteins. It defines the conditions under which they operate. The distribution of saturated and unsaturated lipids is not static. Membranes are continuously remodeled, incorporating new lipids as they become available and replacing damaged components. Over time, this shifts the balance between rigidity and fluidity. A consistent supply of stable, saturated, and monounsaturated lipids supports membranes that hold structure while maintaining controlled flexibility. A shift toward highly unsaturated inputs increases variability, raising the likelihood of leakage, oxidative damage, and signaling distortion. These changes accumulate gradually, altering how the system behaves under both normal and stress conditions. Mechanical stability, then, is not a fixed property. It is the result of ongoing material integration that determines how the membrane responds to force, maintains gradients, and supports protein function. When the balance between saturation and fluidity is maintained, the system operates with consistency. When it is not, the membrane becomes either too permissive or too restrictive, and the processes that depend on it begin to lose precision. Electrical properties of membranes. Membranes function as electrical components that store, separate, and control charge. The lipid bilayer acts as a dielectric barrier that resists the movement of ions, allowing differences in charge to be maintained across its thickness. This separation creates membrane potential, a stored form of energy that drives transport, signaling, and coordinated activity across tissues. The ability to hold this charge is not abstract. It depends on the physical properties of the membrane, including thickness, packing density, and permeability, all of which are determined by lipid composition. Charge separation exists because ions cannot pass freely through the hydrophobic interior of the bilayer. Instead, their movement is restricted to specific pathways provided by channels and transporters. This controlled access allows the system to build gradients and release them in a regulated manner. When channels open, ions move along these gradients, generating electrical signals or driving transport processes. When channels close, the membrane maintains separation, preserving potential for future use. This cycle depends on the membrane's ability to resist leakage. If permeability increases, ions cross without control, reducing the difference in charge and weakening the system's ability to generate signals. Membrane composition directly influences this resistance. Tightly packed lipids increase electrical insulation by limiting the formation of transient spaces where ions could pass. Loosely packed regions increase the likelihood of leakage, reducing the stability of the gradient. Cholesterol contributes by regulating packing, maintaining a level of insulation that supports consistent electrical behavior. When lipid composition shifts toward greater instability, resistance decreases, and the membrane behaves less like a controlled barrier and more like a leaky interface. The system compensates by increasing active transport, expending energy to restore gradients that no longer hold passively. Electrical properties are not confined to isolated cells. They scale across tissues and systems. Neurons rely on rapid changes in membrane potential to transmit signals along axons. Muscle cells depend on controlled depolarization to initiate contraction. Epithelial tissues use electrical gradients to regulate transport across barriers. In each case, the speed, strength, and precision of these processes depend on the integrity of the membrane that holds the underlying charge. Variations in membrane composition alter how quickly potentials can be generated and how long they can be maintained, affecting the performance of entire systems. Capacitance, the ability of the membrane to store charge, also depends on structure. The thickness of the bilayer and the arrangement of its components determine how much charge can be held for a given difference in potential. A stable membrane with consistent composition maintains predictable capacitance, allowing signals to propagate with defined timing. Structural inconsistency alters this property, introducing variability in how signals are initiated and transmitted. The result is not simply weaker signals, but less reliable timing, where activation and recovery phases begin to overlap or drift. Ion channels and transporters operate within this electrical framework. Their opening and closing depend on changes in voltage, ligand binding, or mechanical forces, but their behavior is influenced by the membrane environment. Changes in lipid composition alter how these proteins respond to stimuli, shifting thresholds for activation and affecting the duration of open states. This modifies how ions flow and how electrical signals are shaped. The system continues to function, but the precision of that function declines as structural conditions move outside their optimal range. Electrical stability requires that gradients be maintained with minimal correction. When membranes hold charge effectively, energy can be directed toward productive work such as signal transmission and coordinated contraction. When membranes leak, energy is diverted toward restoring gradients, increasing baseline demand without improving output. Over time, this shifts the system into a state where electrical processes remain active but operate with reduced efficiency and increased variability. Understanding membranes as electrical structures clarifies how changes in lipid composition translate into changes in system behavior. The membrane is not simply a boundary. It is the medium through which electrical energy is stored and controlled. Its ability to maintain charge determines how signals are generated, how they propagate, and how reliably they terminate. When this structure is stable, electrical processes operate with precision. When it is not, variability emerges because the system can no longer maintain the conditions required for controlled charge separation.